various of waveguide modes. Many waveguide modes, including TE mode, TM mode, and their applications. Okay, but before we start, let me show you what is waveguide. I just show you a large waveguide. How about higher frequency? For example, if you want to use your 5G cell phone, you need a frequency of 28 gigahertz. What is the waveguide looks like? This one. The middle is a waveguide, rectangular waveguide. That's another example, rectangular waveguide. Okay, I will show you. I'll give you a chance to touch this waveguide. That's for 28 gigahertz up to 40 gigahertz. If you want to increase the frequency to a higher frequency, for example, 100 gigahertz, you need a waveguide like this one. Very small, just about 1.27 times 2.5 millimeter. Very small. That's for 100 gigahertz. If you want to operate 1000 gigahertz, that's 1 terahertz. No waveguide at all. No waveguide at all. Actually, we have waveguide, but quite lossy. That means wave can propagate inside the waveguide from this end to this end, and the loss may be 90%. Wave cannot propagate inside. It will be absorbed by the waveguide. So terahertz waveguide is another very important issue for waveguiding. Okay, that's why terahertz waveguide is difficult, very difficult. Terahertz waveguide. Okay, give you a chance to touch the waveguide. 100 gigahertz in this direction. Okay. The middle section. And remember to return these waveguides to me. Okay. Sorry, maybe the same direction. Okay. That's for rectangular waveguide or TE or TM mode. Let me show you another waveguide. We have three waveguides here. Look at this one. This one. This is a waveguide called actual waveguide. It's operated on TEM mode. We will talk about TEM mode right after this section. Right after this section. Okay? TEM mode is much more not easy, not difficult, but interesting. Okay? TEM mode. This one is a waveguide. However, it's an adapter. It's a 2.4 millimeter standard waveguide. Just give you an idea. How much does this one? For this one?
10,000.
10,000 more. More than 10,000 for this one. This one roughly about 30,000 for a piece. For a small piece of waveguide. That's waveguiding section for 100 gigahertz. 100 gigahertz. This small one, so totally roughly about 100,000 New Taiwan dollars here. For three waveguides. And the piece is quite small, so you can easily forget about the parts. So that's very terrible for me, because students don't understand what's this. Looks very small. They have no idea. So they think that's not important. Throw it away. Terrible. 3 sections for 3 parts for 100,000 New Taiwan dollars. For high frequency components, normally are very, very expensive. Just give you an idea. Sometimes it's almost impossible to buy from a foreign country. From the United States, if you want to buy power source high frequency, you need an export license. Okay? That means it's related to the defense. Therefore, this part is quite important. Let me reiterate. Okay, I will keep this one. That's for you. This one is, this is the first time for me to become a YouTuber. Also, it's new for TAs. TA are not familiar with minimize the file size, improve the quality of the video. So it takes a much longer time for us to learn. It's a new learning, it's a new knowledge. We have to learn a lot of things. So we are still not familiar with the process. So we are sorry. Probably, hopefully, in a week or 2, we can familiar with the process and can upload the file right after the class. Right now, we spend a lot of time to process the video because file conversion, file upload takes about maybe 30 minutes up to 1 hour. And TA has extra loading just for the video. So, okay. Okay, so now let's talk about Waveguide. We talk about Waveguide, we have some assumptions. We talk about uniform Waveguide first. So, we talk about infinite lengths. Infinite lengths, very, very long. No reflection at all. Wave can propagate inside. And the other is a hollow conductor. So conductor is outside. Inside, maybe air, maybe nothing, maybe vacuum, maybe dielectric material. Normally, inside is nothing inside. Occasionally, we will have some dielectric material inside, or we will have some ferrite material inside. But for most of the case, nothing inside. Okay, so lucky. So it's uniform, linear, and isotropic. And material inside is, in general, complex number. Okay. And conductor, just normal conductor, not superconductor. Yes, somebody try to use superconductor as a waveguide material. But you know it's expensive, right? So normally we use copper or aluminum. Sometimes copper coated with silver. 镀银. That's high-end device, like this one. Okay, depends on frequency. Okay, but most of the case, we prefer aluminum or copper. Okay, aluminum, the problem of aluminum is they have an oxide layer. So they will have some extra loss. But for copper, yes, they will have CuO or oxide layer. It's still not good, but at least for most of the case, copper and aluminum is good. Therefore, for synchrotron radiation, they use aluminum waveguide. For most of the vacuum electronic device, we use copper waveguide. That's high conductivity, oxygen-free copper. That's expensive. That means expensive. High conductivity, oxygen-free waveguide, copper. Okay, that's expensive. Roughly about 3 times expensive than normal waveguide. In Chinese, its name is 无氧铜。无氧铜比红铜那个黄铜贵很多的 ，much more expensive. The total concentration, the purity of the copper, roughly about 99.99% copper. Okay, that's for copper waveguide. And since we have no current source inside, so no rho, no Z, happy life. Okay, from this equation, we can derive the wave equation. The wave equation for electric field and wave equation for the magnetic field. So if somebody asks you to derive the wave equation without source, that's easy. Doing, and you got these 2 equations. Okay? And then, what's next? Let's separate them. You know, separation of variable is the most common techniques we use almost every day. So next step is separate them. This is time dependence, minus I omega t. And this is z dependent, I k z z. How do we know? Because we know the waveform is exponential, I k z minus I omega t. That's propagating wave in z direction. And then we separate them, transverse coordinate. So we separate them into 4 variables, 3, 1, 4 variables. Separate them 1, 2, 3, 4. But remember, this is a phasor, a 3 component, EX, EY, EZ. Okay, but depends on transverse coordinates, X, Y, X and Y. Okay, so just give you an idea. Coordinate transverse to Z, X, Y, or R theta. And KZ here, in Jackson just use K. Okay, but for most of the case, people use KZ. KZZ. Okay, that means the Z component of K. Because later on we have X component, we have Y component of K. We have KX, we have KY. Therefore, we use KZ here because it's very common and we can easily confuse. And in this equation, omega KZ are in general complex constant. But we prefer omega to be real because this is the frequency domain, so we can control the frequency one at a time. And then we can use the Fourier transform to combine all the components back. Okay, so one frequency at a time. And omega KZ are both positive. That's definition. So how to express minus sign, negative? We just add a minus sign here, minus KZ. Okay? So this is plus, this is minus. We know this is forward wave. This is backward wave. Okay. If you use IKZ, then it will depend on the sign of K. K is positive, yes, forward wave. K is negative, yes, backward wave. It depends on the sign. Okay, if you use this notation, be careful. Okay, so what's next? Next one is we can simplify this calculation a lot because they can separable, time dependent, G dependent, and this one approach is separate into transverse coordinate plus this one. So we can rewrite this equation, rewrite the wave equation into this form. Okay? Because of this one, we have this one, have minus sign omega squared. So give us this one. And this one separate into two parts, transverse KZ. Okay? So we can, this is EX, EY, and EZ. Remember, EX, EY, and EZ. Let's choose Z component. For our convenience, just choose Z component. Why not X? Why not Y? Up to you. You can choose X or Y. Doesn't matter. Doesn't matter. But for most of the case, people choose Z. Some people will choose X. But most of the specialists in this field choose Z. Okay? Z component. In that case, we can solve the Z component from here or here. EZ, BZ. Okay? Looks like simple because it's EZ and BZ, and we can use the boundary condition to determine everything of Z component. Okay? Looks okay. How do we determine X component and Y component? EX, EY, BX, BY, how to determine? Okay, if we want to determine other components, we have to do something. Let me remind you by using Griffiths. Griffiths lecture note. Griffiths talk about waveguide. We just use the simplest coordinates. That's S, Y, Z, Cartesian coordinates. Here, we will use cylindrical waveguide. Cylindrical waveguide, not just Cartesian. But the idea is quite similar. So if you don't understand a cylindrical waveguide, okay, don't worry. Just go back to Happy Life, Cartesian waveguide system. You will have a better understanding. Okay, we know that's a good assumption. Inside the waveguide, nothing. No E field, no B field. Okay, but now we know the wave will slightly penetrate into the waveguide. Slightly. A few microns only. Okay, so just terminate on the surface of a metal. Okay, so, but this is a good assumption. That's okay. Inside the waveguide, so for microwave, millimeter wave, far infrared, terahertz wave, visible light, yes, nothing inside. No electric field, no magnetic field. Okay, so this is a pretty good assumption, but not for low frequency. For 60 Hertz, this assumption is incorrect. Incorrect. Okay? Just keep it in your mind. Depends on frequency. That's why it's complicated and can be easily confused. The boundary condition at the inner wall, tangential electric field is 0. Normal magnetic field is 0. That's still true and almost always true. Okay, because we have free charge. Free charge will balance on the surface of the waveguide. So therefore, parallel component on the surface of waveguide will be 0. Okay, normal component will be 0. So that's reasonable. And once again, separation of variable. Separate them into time t, z, s, y. Okay? Once again, the same process. We use separation of variable over and over again. Okay, by doing so, we have, this is the wave equation without source terms, without rho free, without current free, free current, free charge, nothing. So we have this one, but we make a simplified symbol. That is epsilon and mu. We express as epsilon mu. That's the velocity of the wave, but it's denoted as c. Don't be confused. It's a speed of light? Yes, if this is epsilon 0, mu 0. But if you have some material inside, it's not. Okay? For example, if you use some glass or quartz or Teflon or dielectric material such as aluminum and aluminum, that's different. Aluminum means 铝. It's a metal. Aluminum means 氧化铝, Al2O3. That's dielectric. Okay. So one is for metal, the other is for dielectric. Okay, so these two can be rewrite into 6 equations. 1, 2, 3, 4, 5, 6. 6 equations. Next step is, since we have the ability to calculate z component, EZ and BZ, next one is to derive other component from z component. How to do that? Actually, not very difficult for Cartesian coordinates. Try to derive this equation, this relation by yourself. For Cartesian, it's relatively easy. You can practice. Later on, I will give you a much more difficult challenge. That's for any coordinates. Much more difficult. Well, this one is easy. It's good for text because it takes about 2 pages, 1 or 2 pages at most, and much easier to derive this relation. But the idea is you can express ESEY, ESBY in terms of z component. Let me show you how to do that. We have, for example, we have Bx, and we take the Bx, we can take the Bx partial z, partial z, and this one partial Ez, partial z, and we can substitute these terms with others. Okay, and then combine, then you can form these relations. Try, not very difficult for S, Y, Z components. And so EZ, BZ can be derived from these relations. Okay, what's next? Okay, we will classify them into 3 types. One is EZ equals 0. That means no Z component, no electric Z component. So all the field is in the transverse component. So therefore, we use TEMO, transverse electric waves. Wave, electric field just in the transverse because no EZ. Second, BZ equals 0. So that's transverse magnetic waves. Transverse magnetic wave. no BZ component. Last one is EZ equals 0, BZ equals 0. Nothing. So you say, so the trivial solution is 0. But remember, if this one is 0, 0, 0, 0, 0, the denominator is 0, numerator is 0, 0 divided by 0, undetermined, right? 0 over 0. What's that? Okay? In that case, you should go back to the previous page, starting from the very beginning. Okay, starting from the Maxwell equations. Okay, so today we will talk about these two, and next time we will talk about TEM, transverse electric and transverse electric and magnetic waves. Very similar to plane wave. Actually, plane wave is a special case of TEM wave. Plane wave is a special case. Okay, so let me show you how to derive this equation. It takes about 3 pages. Very difficult. I agree, very difficult. However, I write it down so it's much easier to understand. If you try to derive this equation by yourself, just give you my experience. I derive this equation over and over again. Each time looks like new to me. I forget how to derive this equation almost every time. Okay, so that's why I write it down. I write everything step by step. So next time I don't need to start from 0. I can start from here. Much easier to derive. Okay. So I won't request you to derive this equation by yourself because it's difficult. So I hope you can understand the logic, how to derive this equation. And the most important is how to use the result. Okay? So don't worry about these 3 pages. General approach. 1, separation of, not separate, transverse component, Z component, EZ, transverse component, B component, and then transverse component. This is gradient. Gradient or del, transverse component plus Z component. Okay? And after operation, we got plus minus IKZ EZ. Because Z dependent is exponential plus minus IKZ Z. Okay? So first, this is Ampere's law or Faraday's law. Which one? Pardon?
Faraday's law. Faraday's law.
Oh, Faraday's law. Remember? Changing magnetic field will induce electric field. Changing electric field will induce magnetic field. Okay? So from this law, we can rewrite into this part plus this one plus this one. Not plus, equals I omega this one. The same, we can use the same approach. Separate them. What's next? Next one is we should divide it into two parts. One is the parallel to z component. The other is perpendicular to z component. We separated them into two parts. Curl gradient, curl of transverse, curl of E transverse will be parallel to EZ. Ready? Okay. We will use this relation, but keep this in mind. S component, Y component, S component, Y component. S curl, EX, nothing, right? S gradient X curl, curl EY, yes, in the Z component. Y, nothing. YX, oh, YX in the minus Z component. So therefore, they must be parallel to the Z component. Okay, keep this in mind, this is very important. Second, transverse curl EZ must be perpendicular to the Z component. That's clear. For example, XZ in the minus Y, YZ in the X direction, right? So must be in the transverse perpendicular to the Z component. So I use a red color to indicate that is quite critical because people will be easily confused here. Students will be easily confused. Okay? Now, we can separate this equation into transverse component and Z component. First, let's take the transverse component. That's equation 15 and 16. Transverse component of these two equations. Then we got this one, transverse component, and then use these properties. We got these two equations. These two equations tell us EZ, BZ, and their relations between transverse component. Okay? Next step, rewrite this equation again. Rewrite this equation. Okay? Since EZ and BZ can be solved from equation 14. Check equation 14 again. This is equation 14. Okay? This looks like a Laplace equation, two-dimensional Laplace equation. Actually, the without these terms, yeah, it's Laplace, but we still have these terms. Okay, so this we can solve this one, EZ and BZ. So what's next? With EZ and BZ, we can calculate E transverse and B transverse from these two equations. How to do that? These two equations are algebraic, 代数的. Yeah, because just operate on this one and operate on this one. Others are, okay, others not differential, not integration, no differential, no integration. Okay, so it's not a differential equation. We can manipulate. We can rewrite this equation into and eliminate BT, and we can express ET in terms of, we can eliminate one terms here. How to do that? Just times this one to this one, and replace this one with this one. In that case, we have transverse component, and z component. Okay? Transverse, E transverse, because we times this one. EZ first. Okay, so we times this one. EZ curl of these terms, this one. EZ curl of these terms, this one. And EZ curl of this one. Okay? This one can be rewrite into two equations. This one, just this one. That's the part one. Another is part two. Luckily, this one is 0, so we have this one only. This one can work curl on this one or curl on this one. But it's a Cartesian, so it's a constant. Z component is a constant direction, always in the Z direction. So give us nothing. Okay? So we've got this one only. And this one, EZ curl gradient, curl EZ, and cross, EZ cross these terms, It's not an operator, just a outer product. Okay, so it's cross. And this one is 0. And this one gives us one thing, minus ET. Okay? Looks okay. Eventually, these terms, right-hand side move to the left-hand side, and the left-hand side move to the right. So these terms we have this one and this one. This one here, and this one comes from here. Okay, a plus minus. Plus minus becomes minus plus. Okay? So from this equation to here, we need to use this process. This is a hint. What's next? This one is substitute this one. Substitute I omega EZ into here. So EZ, E transverse. BZ, E transverse. So E transverse can be rewrite into, can be calculated from EX, EZ and BZ. That's it. Okay? And this part can be rewrite again. Transverse BZ curl across EZ. Just move here. And we know this one operate on this one, give us nothing, 0. Okay, so this is not curl. From curl of these terms become this one cross this one. Maybe I should explain in Chinese again. 这边一开始的时候是曲度，对不对？这个 operator 会 operate 在这个东西上面，但是一旦 operate 在这个东西上面之后，它就给我们这个东西乘以这个东西，它就变成两个东西了，外基 outer product。OK，outer product 从本来会咬人的，只要咬完之后，它就没有攻击性了。没有攻击性了之后，你就可以把它变成简单的外基。OK，and then we still have BZ, we have EZ, we have transverse, we have another transverse. And how to do that? We can multiply equation 20 by I omega, because we have I omega here. So I omega curl T BZ EZ, move this term to here, and this one IK plus minus IKZ, these terms, plus K squared, KZ squared. Because of this one give us a minus II squared. minus 1, and minus plus minus 1. So eventually, we give plus kz squared. And the right-hand side, because of I omega to move to here, we have a minus sign here, and we have I squared give us another minus 1. So mu epsilon omega squared. Okay, good news. Move to here. So we got these relations. Just 3 pages. We got these equations. So next step is move this one to here, to the denominator. Okay, we got it. Not very difficult. That's not true. Okay, actually it's very difficult. Try, you can try to derive this equation by yourself. You will agree with me. That's difficult. I write everything down, looks easy, but if you try to derive this equation by yourself, you will find that's not easy. Okay, I will give you a chance to practice. Try to derive this relation by yourself. You can follow all the steps one by one. Just follow all the steps. It's open book, so you can, it's open book and take home. Okay, try to derive this equation by yourself. Try and return the paper this Thursday, and you got 1 extra points in total. Okay. Maybe I should give you something to write, some template. All you need to do is use we can simplify the process. Use an A4 paper and write your derivation carefully. Remember to write your name and your student ID and return next time. Okay? Of course, you can return to TA right now if he remember. Okay. I just tell you, class participation can be made in several forms. You can return your research study about this field, about these topics, about any topic related to electrodynamics. So 5 points is extra for you for free. Try your best to get 5 points as early as possible. Okay. Try your best. That's actually not difficult. For example, our staff just give me a report last semester. We got 5 points easily. Okay. This is an example. Try to derive this equation by yourself. Follow the step one by one. I do not expect you to derive this equation starting from 0. I just tell you, you can follow the logic, follow the process, derive this equation step by step. Okay, remember we just separated them. Transfer component, easy component, and put everything together. That's it. And make sure one is in transverse component and the other is in the G component. That's it. So actually, if I give you everything, then it looks easy. Okay. We have discussion here. Maybe we should stop for a few minutes. Just think about it, and if you have any question, you are welcome to ask here. Any questions? I'm sorry. Maybe we should take a photo now. Just to make sure your position is okay. Okay, here. Look at me. Up. Smile. 1, 2, 3. Okay. Another one. You is up. Okay. 1, 2, 3. Let's not check your attendance. Don't worry. Don't worry. Online learning is pretty good, right? If you feel uncomfortable, for example, you have a sore throat, coughing, you can stay at home. That's 100% okay. But keep in touch with professor and your friends. Totally, you are okay and maybe healthy, but because of some symptoms, so you have to stay at home. That's 100% okay. Self-health management is quite important. Okay, let's move on. This is the discussion. We have a transverse component and decomponents in these two equations. They are all function of transverse coordinates. Mu and epsilon in general are complex. So imaginary part of mu and epsilon normally represents dissipation, conductor loss, dielectric loss. So we actually have many laws. Conductor is not perfect. It's just a normal conductor. So we have conductor loss come from conductivity. We have dielectric loss comes from imaginary part. We have magnetic loss come from here. We have radiation loss. For example, this is K band, and we join them together. The contact cannot be perfect. So they might have some kind of radiation loss, some kind of leakage. So this is some kind of loss. So later on, we will consider all the loss. And Yongjian, this one is about 10,000 Taiwan dollars. And this one is more expensive. I don't quite remember, maybe 15,000. Where is the last one? Okay. Last one is directional coupler. Okay. That's directional coupler. Actually, it has many holes. 1, 2, 3. That means the wave coming from this direction will pick up from this hole, maybe 1% or 0.1%. And most of the wave will propagate from here to here. And reverse will be no signal from here. So it's directional coupler. Make sure wave can propagate in this direction and couple from this direction. So you can measure, if you have 4 holes, 1, 2, 3, 4, you can couple 4 wave and backward wave. And then you can determine your power. Okay? Looks difficult, but just give you an idea. Actually, to design this one is relatively easy. Okay, just kind of use the idea of dipoles. You can design this one easily. This one is for communication, is for multiple purpose. That is not difficult, but can make a lot of money. You can check the website, 森达科技，他们就是靠这个赚了不少钱。EPS 好像有到6块吧，还是5块？我们都会做啊，可是就是不是我们赚钱。Roughly about 10 years ago, I request my student to design and fabricate this kind of directional coupler for their first exercise, and they can easily achieve high performance waveguide easily. Okay, so that's not very difficult. Okay, next one. If we have BZ equals 0, we have transverse magnetic. We have EZ equals 0, we have transverse electric. And if EZ and BZ are both 0, then we have transverse electric and magnetic wave. So I will summarize this one as here. For a waveguide, we have TM mode. If BZ equals 0. And so if BZ equals 0, we can simplify the notation into gamma squared equals to this one. So transverse E equals this one. Simple, right? And transverse T becomes this one. And ET is here. Epsilon omega over KZ. We can define something like KZ over epsilon omega. This is E, this is H. Remember, from Ampere's law, H gives us the current I. From this one, we can calculate voltage. Voltage, current, Ohm's law. So the ratio should be ohms. Yes. So we define something called wave impedance. Actually, it's a ratio between E and H. It's not I and V, so you cannot say resistance. You can say it's a ratio between E and H. So you say another name, impedance. However, the dimension of impedance is exactly the same as resistance. Dimension is this one. Ohm, OHM. They have the same dimension, ohm. Okay. So the ratio between E field and H field, we call impedance. The idea is quite similar to the resistance. Let me show you. Just give you an idea. For plane wave propagating in the air, the impedance is about in the air. Okay? But for this one, this TEM wave coaxial, the impedance is it differs a lot. What happens if the impedance is not the same? E field, H field, E field, H field. For example, if you have two regions, this one is 377, this one is 50. That means if you have same current, your E field will be different. If you have the same electric field, your H field will be different. What will happen? Reflection. This is impedance match. If their ratio is the same, then they can propagate from one region to another region easily. Okay, but if their ratio is different, they have to match the boundary condition. So part of the wave will reflect back. Therefore, impedance match is quite important. I just give you an idea. This one will be very important later on. Okay. Therefore, if you want to receive some signal from the air, you need a different antenna. For example, some kind of antenna like this one. This antenna roughly about 300. So wave can absorb into your TV. Okay, that's for TMO. How about for TE mode? TE mode is quite similar. TE mode, TE, we have EZ equals 0. So we got these equations, and we got this one. Okay, that's for TE mode. Once again, we have the impedance. Interestingly, impedance for this one is omega divided by K. This is K divided by omega. So people will be easily confused. Actually, I personally confuse all the times. So I will check my lecture note or check Jackson almost all the time. So I do not expect you to remember everything. That's impossible, right? I expect you to understand how to derive these equations. How to derive this equation. Maybe just tell you a story. IQ test. What is the IQ of 柯文哲? Anybody know? 柯文哲不是说他超聪明的吗? What is the IQ of Taipei Mayor, Professor Mayor 柯文哲? Anybody remember? 有人知道吗
157，
对吧？那个红军都记得。柯文哲号称他的 IQ 是157，你知道我有多少吗？要不要猜猜看 ？What is the test result? IQ test result of?
回答。
OK， 好不好？
会吧？
哇，
真厉害。
Much higher than him. But remember, that's for military service. If you want to be a lieutenant, you got to pass the service, but you got to pass the test. At that time, the test takes about 1 hour. And if you finish, you can leave in 30 minutes. And I finished everything and returned the paper in 30 minutes. And the officer looked at me. This man looks like stupid or smart. I returned the paper without check because I know the minimum requirement is the minimum requirement for the IQ test is 110. I know I must greater than this one. Okay, so I do not check my result because I know I must be greater than this one. If I check, probably will be greater than 180, but maybe lower, maybe lower. No one knows. Okay. Looks like very smart, right? Looks like, just looks like. I know I'm not good at remember names, but good at understand physics, good at have a much better than my 3D imaging is much better, but 2 dimension, 1 dimension is not good. My memory is good for 3 dimension or 4 dimension, but not for 1 dimension or 0 dimension, not good at all. Okay. How to determine Z component? Easy. You can easily use the boundary condition here. How to determine BZ? Okay, once again, or HZ. HZ. You can use another boundary condition. This one. Why? Why we use different boundary conditions? That's because you can use exactly the same boundary conditions. The result will be the same. Will be. But for our convenience, we prefer use EZ because we know EZ will be 0. And for this one, sometimes, because this one will relate it to this one will relate it to this one. HZ versus the normal components. So this one will be related to this one. So remember, we say normal H should be 0. The current, surface current, just flow on the surface of a conductor. So magnetic field will be, or flow in this direction. Magnetic field will be in this direction. So just tangential, no perpendicular component of magnetic field. Therefore, we will use the same properties here. I know probably you have no feeling here, so I will give you some example. Next time, if you have a chance to deal with the problem associated with waveguide, just go back to this page. Go back to this page and start from here and here. Okay? Much easier. That's good for uniform waveguide. For arbitrary shape, okay, always true. Okay, so it becomes an eigenvalue problem. Either equation 21 or 22 constitutes an eigenvalue problems. The eigenvalue is gamma squared will be an infinite set of discrete values. So this eigenvalue will be a lot of discrete values. It's a set. Something looks like quantization, like quantum mechanics. quantized because of boundary conditions. Boundary conditions will quantize this value. Okay, we will show you very soon. This one is not continuous for waveguide. It's continuous for the air, but not continuous for the waveguide. So it will be fixed by the boundary conditions. So I prefer to compare this discrete value, this case, with quantum mechanics. Okay? And B shows that E transverse is perpendicular to B transverse. Yes, in this case, it's true. Just like plane wave, EH, E cross H, E perpendicular to H. Yes, in this case. And ET and BT are in phase. Just like they always increase. Yeah, they are in phase. You might wondering, if this is not true, what will happen? Reflection. Okay. If this is not true, what will happen? Loss, transmission loss. Okay. So you can determine from the behavior of the wave from these properties later. Okay. That's not always true. That's true for propagating wave only. In general, not always perpendicular, not always in phase, not always. Okay, for example, in a cavity, E field and B field will change out of phase. E field increase, B field decrease, D field increase, E field increase, like a swing. Kinetic energy increase, potential energy highest, kinetic energy, potential energy, always changing. Okay, but total energy should be conserved. Okay. And that's dispersion relation. Dispersion relation is the relation between omega and k. That's to be determined. Go back to this one. This one, gamma squared, that's quantized. So we have omega squared, we have kz squared. Relation between omega and kz called dispersion relations. Okay? Dispersion relations. So obviously, we will have a lot of dispersion curve because of this one. Each curve corresponds to different mode. What is mode? Let me show you. For example, this one. This is TE11 mode. This is amplitude. And that's surface current. So surface current for TE11 is 30, right? However, for TE01 mode, flow in this direction, flow in this direction, or this direction, or this direction. For TE01 mode, and the field pattern, electric field, like this one. And you can see here, this is current, so magnetic field will be in this direction. And this is electric, you can find the relation between surface current and E field, B field. Okay. That's TE mode, that's TM mode. TM mode, TM11, TE11, different field patterns. That's electric field, so different field patterns. What is this field pattern looks like? Like a pig nose. 猪鼻子不像吗？ Like a nose of a pig. Yeah. And TM01. TM01, we have electric field, highest here. For TE01, we have electric field, highest here and in this direction, and magnetic field in the middle. You can imagine, we have current, so we have magnetic field in the middle. Changing magnetic field will induce electric field, right? So we have electric field here, we have magnetic field here, we have series current here. Everything is related. Okay, how to do that? You can use a high frequency structure simulator to simulate everything. Okay, just give you another idea. So we know this one is independent of the gate. As you can see here, if we have a gate for TE01, nothing changed, still 100% transmission. But if you have other modes, you have other mode inside, that will change a lot, So let me show you this slide. Let's rotary join. It's rotatable. For example, if we have a radar, and radar will rotate in this direction, and then rotate in this direction. So you need a rotatable, and wave can propagate from this one to here. And so you need wave, incident wave to here, and reflected wave to here. You need multiple channel. Therefore, you need multiple modes. So this research is performed by these students. We bought them. Okay. Yes, I will stop here. Okay, actually, later on, we have more than one invention. We have multi-channel. We can up to 4 channel. 4 channel. One is radiation. The other is, one is transmission. The other is receiving. And then we will lock, 锁定. Last one, I don't. We can design multi-channel rotary joint. Based on this idea, we can derive the waveguide modes for many, many applications. Okay. I should use some music here, like transformer. Doing, doing, doing. Okay, we have a bearing, and this is a waveguide made of copper. Just 4 piece, just 4 piece. So it's good for rotatable. It's a rotary joint. And higher frequency. Right now, we can generate up to 400 gigahertz in our lab. 400 gigahertz. Okay. I will stop here. Any questions? Any questions? TA will give you 2 problems, right, today? Okay. Any questions or comments? We will talk about waveguide. How about cavity? Okay, for example, this is a waveguide. If this end is closed with metal, and this end is closed, then it's cavity. So waveguide and cavity are quite similar in physics. Waveguide is quantized in this direction, but if you cross this end, then it also quantized in this direction. Everything is quantized. The resonance frequency will become quantized. Okay, it's completely quantized by the geometry. S, Y, Z have 3 quantization numbers. Okay, but the problem is actually Schrödinger equation and Maxwell equation looks very similar. However, Schrödinger equation we have spin, extra spin, but Maxwell equation just 3-dimensional. How about the last one? If we want to unify these 2 equations, how do we deal with the last one? Or maybe that's a spin. Principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. But for EM wave, we just have 3 quantization numbers. So for time-independent case, these 2 Schrödinger equation, Maxwell equation looks very similar for time-independent. But for time-dependent, not exactly the same. That's another story. And that's very challenging, very difficult to answer. We need someone like him. But he passed away. Maybe we need someone like you. You can answer why. You can answer the 4th quantum number for Maxwell equations. Okay? We have a new clock. Any questions? We still have 2 minutes, 1 or 2 minutes. No question? Everything looks easy? Yeah, just looks easy. If no other question, I will stop here and I will invite our TA to give you 2 examples. Okay, see you next time.
Okay. So now is the TS lecture time, and this is not the formal lecture. So if you have any other things, you can just leave. Yeah.
I can leave. See you.
Okay, and in this semester, I will use the projector to demonstrate the problems because in that semester I find the blackboard is too slow and I don't have enough time to talk all the problems. Okay, and today I will demonstrate the problem 8.2 and 8.3. So, and unfortunately, the teachers don't talk about TEM mode of the waveguide, but these 2 problems are TEM mode. So, the problem 8.2 is that there's a transmission line consists of 2 concentric circular cylinders of metal with conductivity sigma and the spin depth delta, and it looks like this one, this circle. The dark one is the conductor, and the light one is the dielectric medium. And if you have any question or don't understand, just raise your hand and make some noise, because yeah. Okay. And the waveguide is filled with a uniform and lossless dielectric medium. So the dielectric constant mu and sigma, mu and epsilon are real because they are lossless. And the TEM mode is propagated along this line. And the problem A says, please show the time average power flow along the line is in this form. P equal to blah 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 blah. Yeah. And H0 is the peak value of the azimuthal magnetic field at the surface and of inside conductors. Okay. So from the textbook, page 358, we know the TM mode, the electric field will satisfy these two equations. The curl of the electric field is equal to 0, and the divergence of the electric field is equal to 0. So actually, the TM mode in the waveguide is just an electrostatic problem, just like in the last semester. You only need to solve the boundary condition and don't need to care about any other dynamical things like what is the time dependence and other things. You just solve the boundary conditions and boom, you get the answers. Okay, so in these problems, it is coaxial cylindrics. So the electrostatic electric field in polar coordinate has the following form. E is equal to the A over rho in the rho directions. And because it is very easy to get from the Gauss law, so I will not show how to get this form. If you have any problem with this, I recommend you to see the last semester's lecture notes. And since this is a TEM mode, so the magnetic field BTM has the following relations. BTM equal to the constant and z direction vector across the electric fields. And in the uniform dielectric medium, H is equal to B field divided by mu. So we can find H is equal to this one. And if you need to take a photo and other, it is okay. And from the problem, we know that the peak value of HTM is H0. So the peak value H0 is equal to the constant times A divided by little a. And this little a is the radius of the inner conductors. So with these relations, we can determine the capital A is equal to this. And then we get the TM modes electric fields and TM modes magnetic fields. And to calculate the time average power flow, we need to know the Poynting vector of these systems. The Poynting vector S is equal to 1 over 2 and electric field cross the H field. And since it is SU the power flow, so the direction is not quite important in this case. So maybe in the test you will have an extra minus sign, but I think maybe it's okay. Yeah. And the power flow in the z direction is the Poynting vector dot the z direction unit vector and integral over the flowing area. And so then you will get the final result pi times the H0 square and lot of geometric-like constant. And this is the picture of the systems. Basically, it's just like two concentric and two coaxial cylinders. Okay. Then problem B is to ask you to calculate the power loss in this system. Since the dielectric is lossless, so the only loss in this system is from the conductivity, the skin depth of the conductors. And you can find this formula on your Jackson's textbook or the teacher's lecture note, and in the section 8.1. The power loss per area is equal to the effective surface current density divided by this constant. The sigma is the conductivity and the delta is the skin depth of these conductors. And in this problem, the power loss per volume is in this forms. The dl is the length in the. Oh, I need a photo here. dl is the inner circular length, and dl in is the inner circular length, and dl out is the outer black circular length, but the projector is not so clear here. So with this formula, the power loss per length is equal to the constant and the effective surface current integrate through a circle inside at the surface of inside conductor and outside conductor. The integral region is this red circle and the black circle here. This is the integral region. And the current in the effective surface current is induced by the Tn magnetic field. So we can calculate the effective surface current from the H field. And after the integration, we can find that the power loss per unit length is equal to these things: pi divided by sigma delta and times h squared, h0 squared, a squared, and 1 over a plus 1 over b. And from problem B, it is initially give us P of z is equal to P0 times the exponential minus 2 gamma z. So the gamma is equal to this 1 over 2p times dp dz. And the power loss, minus power loss is the dp dz, because the power is decreased along the z direction. So how many power you decrease is the loss you have. Thus, we can use the formula of gamma here and plug the p and dt dp loss into the formula, and after some algebra and cancel the common coefficients, we get the gamma is equal to these things. Okay. Now, the problem C is asked us what is the characteristic characteristic impedance of these systems. The characteristic impedance of this system is defined by the voltage difference between two conductors divided by the current. So we need to compute the voltage difference between two cylinders as well as their current. The voltage difference between two cylinders is just integrate the electric field along the row directions. So since the dependence of rho is just 1 over rho, so after the integration you will get a log here. Just like the infinite long wire problems, and infinite long wire charge distributions potential. And now, we already have the voltage difference. Now we need the current in the conductors. And there are two conductors. But after the calculation, you will find no matter you calculate the inside conductors or outside conductors, you will get the same current. And this is quite natural because the charge is conserved. So you totally will have a different directions current. So for the inside conductors, the surface charge density is equal to H0 times the directions, and the total inside current is just 2 pi A times H0. And the same, the effective charge density at outside current and at outside conductors is equal to the H0 times A divided by B. And after the integration, you will get the same value, 2 pi A times H0. So this system, the characteristic impedance of this system is 1 over 2 pi times this dielectric constant and log B over A. And problem D is you want us to calculate the series resistance from the power loads and the inductance of these systems. So if you want to calculate the resistance, then you can, because this system only have the only power loads comes from the conductor's resistance. So the total power loads is equal to the 1 over I squared times R. This is just like the maybe in general physics, the power of a circuit. So 1 over 2 times I squared R is equal to the power loss. And the power loss is calculated in the part C. So you just, and the current is just calculated in the part C here. The current is have already calculated, and the power loss are calculated. So you just plug them in and divide them. You will find that the resistance of this system is equal to 2 pi sigma delta times 1 over A plus 1 over B. And for inductance per unit length is quite a little bit hard, because in this system we have if you want to calculate the inductance, you need to calculate it from the energy stored in the magnetic field. But since our conductor is not perfect, so there will some magnetic field leak into the conductors. So for the energy stored in the magnetic field, you will not only need to calculate the volume inside in the waveguide, you also need to calculate the magnetic field inside the conductors. So for the magnetic field inside the waveguide, the energy density U little UV field is equal to mu over 4 times H squared. And this formula can be found in the last semester's maybe chapter 5 or more earlier. So the magnetic field energy is the energy density integrate over an area. And you will find this value is mu over 2 pi times h0 squared times a squared and log e over a here. And the hard part is the magnetic field inside the conductors. And for the magnetic field inside the conductors, we have the following approximations. We approximate our magnetic field exponentially decay into the conductors, and the decay length is the skin depth delta, and the direction is in the phi directions. And since we have two conductors, one is inside at the center, and another one is outside. So so we need to calculate both inside and outside magnetic fields. Hence, the magnetic field inside the conductor is mu c over 4 times h squared, and the integrated region is the inside area. So, and since the skin depth is very small, so instead of integrate over from 0 to a, we can approximate this integration to integrate from 0 to infinity, because this skin depth is very small. So any number divided by a small number will become very large, so it can be approximated to infinity. After this integration, we can find that the energy stored in the inside conductor is about order 1 delta. And also the energy stored at outside conductor is about just about order delta. So combine all the magnetic field energy, the energy stored in the waveguide, the energy stored in the conductors, we can find that the total energy stored in the magnetic field is 2 pi a times h0 squared times this following constant. And mu is the dielectric constant. Mu c is the magnetic permeability in the conductors. So then you can find the L in the inductance in this system is just like in this form. And this is the problem 8.2. And in this problem, most of things are just like electrostatic problem, and just like in the last semester. So if you are not familiar with the last semester's things, I recommend you to do these problems again, and it will be very helpful to review the electromagnetic static problem. And now the 8.3. Basically, the problem 8.3 is just like the problem 8.2, but the shape is changed. In the problem 8.2, the shape is coaxial cylinder, and in the problem 8.3, the shape is changed to 2 plates, and dielectric medium are just between 2 conductors, like a sandwich, and the thickness of the dielectric is A, and the width of the conductors is D. So, and the problem A asks you to calculate all quantity you calculate in problem 8.2 again. So you need to calculate the power, the loss coefficients, the characteristic impedance, and series resistance, and the inductance per unit length. And all the calculation steps are just like 8.2. First, you need to calculate the electric field, TMO electric field, and after you calculate the TMO electric field, then you can find a Poynting vector. After you have a Poynting vector, then you get a power flow per area, and time reached power. And then since this problem gives you the skin depth constant, so you can find the power loops from the induced by the surface charge. And the characteristic impedance is just the voltage difference by two plates. The resistance and the series inductance is the same. So yeah, the step is just like I said. So for two infinite conducting plane, the electric field is constant, and the constant A is determined by the peak value of H. So after we get the electric field, the magnetic field is just the Z cross the electric field. So the HTM is equal to minus A divided by dielectric constant, and it's equal to H0 F, and it's equal to the H0. This is the problem given. So we can use this condition to solve the undetermined constant A. And after we get the electric field and the magnetic field, we can calculate the Poynting vector and integrate over area. We get the power flow, every time every power flow. And effective surface current is equal to the H0. Oh, sorry. After you get the effective surface current, you can calculate the power loss per area and per length. And then the loss coefficient gamma is just the same. And for the characteristic impedance, the delta V is more simpler because the two plates, the two inductance plates have a constant electric field. So the delta V is just a constant times another constant, and this constant is the distance between between two conductors. So it's A here. And the current is just integrate over the plane, the surface current density integrate over X, and you will get the VH0. So you divide these two quantities, you get the characteristic impedance here. And again, since this system only have the conductor's power loss, so the resistance can calculate from the power loss. So we use the same formula here to calculate the series resistance, and the inductance again is quite a little bit complex because you need to consider the skin depth, the magnetic field inside the conductors. So for the magnetic field in this waveguide, the formula is all the same. And the waveguide energy in the waveguide is A times D times energy density, mu over 4 times H0 squared. The magnetic field inside the conductor is use the same formula, exponential decay divided by skin depth delta. And after the integration and some approximation, I approximate the integration distance from finite to infinity. Then we will get order deltas And you will get the energy is about order delta and order 1. So the total energy stored in the magnetic field is B squared times H0 squared times this following constant. So the inductance in this system is this. And this is problem 8.38. For problem B, it asks 2 questions. If the width of the upper strip is more greater than h, what will happen? And basically our calculation is under this assumption, so nothing happened. Just what we calculate is just in this case. But another case is it asks what about B is much smaller than h? If the B is much smaller than h, then this system will become like these things. The conductor is not just like a strip. It is more like a wire, an infinite wire above a dielectric medium. And this system is don't have an exact solution for now. So the only way to calculate this system is use maybe some simulation software or like HFSS maybe. Yeah. And this thing is so-called microstrip transmission line, and it is widely used in art engineering. So if you have interest, you can Google it. And I find some paper it use the image of charge method and calculate the potential in this infinite series form, but I don't think it is need to. I don't think you should remember this because it's very complicated. And I taught some figure. Yeah, this is the problem B's potential. It will look like this. There are 2 singularities at the conductors, the small conductors, because we use the image of charge method. So there are another singularities. The image one is unphysical, and the potential in the contour plane is look like this. So you can expect there will the electric field is look like this. It will point from one conductor to the 0. 0 is the grounded conductor here, and this is the small conductor above the dielectric medium, and this is the small conductors here. And the electric field will from this conductor and point out to the grounded conductors with the discontinuous here. This is the dielectric boundary conditions. So the electric field line will just like this, a little bit distort in the boundary. Yeah.